All right. Hey everyone. So today we are talking about a new subject, simple harmonic motion. What is this new type of motion? Well, until now, we've sort of looked at just basic single objects that move maybe linearly, or maybe they rotate, or maybe there's a whole bunch of them in a fluid. A whole bunch of small molecules all have their own individual movement. What if an object, let me put this over here. What if an object doesn't move in a straight line or maybe a consistent, rotation, but what if it oscillates? What is an oscillation? Well, an oscillation is something that is a steady repetition of some sort of motion. So you think back before when we were talking about spring motion. There's also we haven't gone too much into pendulums. Think of how a pendulum swings back and forth. This type of motion, it's consistent, it's regular, it's a regular pattern. This is said to be something that is oscillating. Now, take, for example, that pendulum swinging back and forth. If we didn't have air friction, we didn't have gravity, or I think mainly friction in like the bearings or air friction, we would need gravity for a pendulum to swing. But if we had this perfect system, this oscillating motion would continue forever, and it would always be the same. It would consistently move at the same rate. This type of motion is, if it's basic enough, it's not doing anything too crazy, that's said to be called simple harmonic motion. Again, this is seen in a lot of everyday objects. Many springs follow this rule, along with pendulums and many clocks. What we're going to look at for this example is, imagine a spring. So I have this sort of slinky here. And again, imagine if this was the perfect system. This is clearly not the perfect system here in my room. But we have this slinky, and if I were to, let's see where it rests naturally. It's sort of, at this height from, where it's connected up here to my hand. If I were to disturb it in any way, if I was to, maybe pull on it a bit like this, there is that relation, Hooke's law, that is trying to force it upwards. And so if I were to disturb it the other way, if I was to bring it up like this, Hooke's law also says it wants to be forced back downward to that equilibrium position. So it's having this constant change of force in different directions. Let me bring the picture up. Now, what if I take something like this spring and I were to connect a pencil to it? And for my drawing here, I have this spring connected to a pencil. And let's say it doesn't, need other any other types of support, and this is like a perfect spring. We're going to say everything about this is perfect. This is a side view. Side view. We know from before, it follows Hooke's law. Which is just this sort of restoring force, which is related to its spring constant times how far you displace it from its resting point. So like pulling it a little bit, there's just a little bit of force pushing it back up. If I displace it a lot, there is a large force wanting to force it back upward or to its equilibrium point. What else can we say before we get into if this object is oscillating, it'll have if it's oscillating at a regular rate, it's having its own frequency. Let me also add in here the equation for frequency in case we have forgotten. So I'll just put it right here, F. So this is frequency. Yeah, I'll put it right here. Okay. So we have just this in this picture example, we have this system, and let's say it's at rest right here, just a certain distance away from the wall. And I could, displace it a little bit. I could bring it out here, but it will want to be forced backwards. Or I could compress the spring, and it will want to be forced back to its equilibrium position again. Let's take this picture and let's look at like a top view. Let me take this picture, and now we're looking at the top of it. And let's go like that. There we go. And what I'm going to do, you can imagine I'm going to, this pencil is connected to, the spring. It's going to oscillate back and forth. Let's say it's perfect, so it'll continue at the same rates forever. So it's just oscillating back and forth in the same position. But I'm going to like drag a piece of paper underneath it. So this piece of paper will get this line drawn onto it. Now this is like an analog for the motion of this simple harmonic oscillator. It has a wave-like pattern, a wave-like representation here, and that's exactly how I can describe its position at any time. Since time is always continuing at a consistent rate, I can predict where this oscillator will be. Maybe, what if I wanted to find out where it was right here? Oh, then it's some obscure position right there. So let's write down. We have position for, position in simple harmonic motion. And this is related to, so the position X is related to A cosine omega t. Try to make that look like an omega. Omega t plus this delta. All right, so I'll define, I ran out of room. We have A for the amplitude. And what we're going to say is all of this is the phase of the wave. I'll sort of, actually, yeah, I'll put this right here. Amplitude, phase. So amplitude, that's pretty easy to see what it is. That's this specific position. Its maximum amplitude is this line right here that I've just drawn, A, and it has a the same amplitude going in the other way, except it's negative. All right, it's easy to wrap your head around. What is the phase, though? Well, the phase, let's try to make this like a dotted line. The phase is, where does the wave begin? There we go. What do I mean by where it begins? You see, I started with the at 0, at this sort of origin right here. I've started at negative A. Why did I start right here? I could have started with a wave that went like that. And by doing this, you see it's shifted over. This would be something with a different phase. It has the same amplitude and it has the same frequency, but it is shifted a bit. So the phase is sort of where you start this wave, where you start measuring from. Okay, I'll define all of this on the next page also. Yeah. Okay. This next page is just a continuation of this thought. What do we have? We have looking at the position. So this is where we have the position. A cosine omega t plus delta. And I said A is the amplitude. Omega t plus delta is the phase. We can say delta itself is the phase constant. So these are all just, or this phase constant is just a value. It'll be like 0, pi, 2 pi. So we have the phase constant. And I'm going to add another one. Omega in this case is the frequency, or I'll say angular frequency. All right. If we have one wave, we can write that equation above as we have one wave, we don't have to worry about the phase. We could choose this to be 0 and make our equation easier, since we don't have to deal with caring about exactly where it starts on this graph. We could choose the easiest position, which is starting at 0. So for one wave, we could say x this is a whole lot less intimidating to look at. But then for 2, if we have 2 waves mapped onto the same grid, then we need to know where they're positioned relative to each other. This is omega t plus, right, there we go. If we want the velocity, in simple harmonic motion, we have, the same way to get there is by having the, so like v of x, and we just take the time derivative of the position. And then in this case, see there's the t in here. We have to take a derivative of time with respect to time. So we get minus omega a sine. And just to keep it general, we'll do the whole thing plus the delta. And acceleration is the derivative of velocity, time derivative of velocity. So I'm just going to say x equals minus omega squared x. Okay. Let's see. From here, we can, find a variety of other things. I'm not going to be deriving all of this. It's simply too much to go step by step by step all the way through. So here we have, I'll just say from here, I'll just say from here we can find out that the angular velocity or the angular frequency is the spring constant over mass. We could also say setting t equals to 0 in all of these equations up here. If we set t equals 0 in an equation like that, we get the initial velocities in a lot of these equations. So it'd be like x, the initial position, x naught, is equal to a cosine delta. And then v naught x is minus a omega sine. I don't like how we'll do omega a sine delta like that. And what else? Just have another also. We can use the initial and final to get this new function for the position. It's related to its frequency. Let me make some more room. Okay. And just throwing equations out here. We have another way to find omega. That is 2 pi 1 over t. This is the period. Over t minus the frequency. So this is saying if we look at the period and compare it with the frequency, we can get pretty much showing how frequency is related to the period. And also this additional way to calculate for the frequency of a simple harmonic oscillator. So a lot of equations, I didn't really connect them. The book does just a few more steps than I have. But at this point, may need these for like a question, but the concepts I'll try to be a bit more thorough. Okay, so we have just a lot of new equations that we can use. I'm not going to go into a problem that just asks to calculate everything. What I'm going to do is do an example that is for a spring, like my example in the beginning of the class today. So we have this spring whose position is given by x equals 5 centimeters. And it's a function, 5 centimeters times the cosine of 9.9. This is 1/seconds, or, I could just say seconds to the -1 times t. So just imagine there's a times sign in there, a multiplication sign. In fact, I think I'll do that. All right. We have this function that expresses the position of this simple harmonic oscillator. What is the maximum speed of this object? Similar to our pencil on a spring example. So what is the maximum speed of the object? When does this maximum speed first occur? After t equals 0. What is the maximum acceleration? And when does this maximum acceleration occur? All right. So to start out, we have this function here. And what this is saying, now this right here, that's the amplitude A. This is cosine, two things multiplied together. So this is omega and t. All right, so we have equals A cosine omega t. This can go into a new velocity function. You just got to take the time derivative. And I'm going to do it of just the, general form right here first. Minus omega A sine of omega t. All right, it's not, now it's not exactly us placing oh, we're going to be doing that in just a minute, right? So now let's place the values for this velocity. We have velocity is equal to omega A sine of omega t. Now, something I'll write a note of on the side over here is, let's see, I'll say the maximum speed. So for that first part, we want to find the maximum speed. The maximum speed v, I'll put it over here, v occurs when the absolute value of this, angle here occurs when sine omega t equals 1. All right. So let's think about this. So if we have that pencil on the spring, it's going back and forth. At the very ends of the, this oscillation, it is at the very ends of the oscillation, it is slowing down. It's slowing down and then going back up. And then up here it's slowing down and then going back down. So it's right in the middle. Let me try to, it's hard to show. So it's right in the middle that it's moving the fastest. So we want this angular, well, hold on. So in order to find the position right in the middle, that's where we set this equal to 1. Okay. All right. Doing that, we just get this new velocity term, A. So that is just saying it equals 1. If we take the sign of, remember, this is not, how do I, so this is, there's parentheses around this. So it's going to be the sign of something. And if you take a sign of any value, it's going to be a range between 0 and 1 if you do it on your calculator. And so the maximum of whatever is in here, we don't quite know what's in there yet. The parentheses, the maximum sign value can be 1. Otherwise, it's going to be some, 0 points, something, smaller value. So that's sort of my reasoning why we want this to be 1. Just say whenever it is, that will be when it's moving the fastest. Okay. Now we have 9.90 omega. So this right here is the omega, and it is an angular velocity. So we'll just say radians per second. Up here, it's expressed as hertz, so it's just 1/2. But since radians aren't technically a unit, I could have them as radians right here. Okay, radians, and times the amplitude, which is the value out in front. This gives us equals 49.5 centimeters per second. Since I don't like that, I'm going to convert if this was meters, 0.495 meters per second. All right. So is that first part. Let's do the next part. It asks when does this maximum speed occur? So we now know what the maximum speed is. When does this occur? Well, what was a condition that we needed? We needed to have this sign value right here to be equal to 1 in order for this in order for this multiplication to be its maximum. So when will this sine of omega t equal 1? That's what we're wanting to find out. So when is sine omega t equal to 1? Well, a sine of what value equals 1? And we're thinking in radians here, so that means that omega t is either pi over 2, it's 3 pi over 2, 5 pi over 2, and so on forever. But they only asked for the first instance when it was its maximum value. So that would just be pi over 2. Okay. So let's take that pi over 2 and we'll go, we'll say t equals, we're just plugging it into here and solving. Or sorry, we're taking this and solving for t. That's what I meant to say. Pi over 2 omega. And so we get pi over 2 times the angular frequency. There we go. And this specific time that is moving this at this maximum velocity is 0.159 seconds. All right. Next up, they wanted to find the maximum acceleration of the object. Okay, finding the acceleration is just the derivative of the velocity term. Vx over dt, and this is minus omega squared a. So let's see. So we're taking the time derivative of this. So just kick out another omega, and this would be cosine omega t. All right, same thing again. So we have this multiplied by a cosine, and this cosine value is going to be any value between 0 and 1. Sort of similar to that, my reasoning for making this sine equal to 1 up here. So whenever it is a 1, it'll be 1 times the rest of it, which is the maximum. So therefore we require that cosine, I'll just put over here, say cosine omega t equals 1. Whenever it does, it'll be moving it will have its largest acceleration, its maximum acceleration. A max is squared a. And since this is a harmonic oscillator, it's going to be oscillating back and forth, it doesn't quite matter where the direction. It just said maximum acceleration. It can be negative or positive. At this specific point, I'm just taking like an absolute value. So we have this 9.90 radians per second squared times the magnitude, or sorry, times the amplitude. And that will be equal to 490 centimeters per second squared. And I don't like those units, so I'm going to say 4.9 meters per second squared. That's a bit more easy to wrap our head around since we've been doing that the whole semester. And finally, when does this maximum acceleration occur? Well, what was the condition that we required? We said, say cosine omega t is equal to 1. When does cosine of t, cosine omega t equal 1? Well, that's when omega t equals 0, pi, 2 pi, so on. What's the first one that isn't 0? So we're not going to take 0. We're going to take that first one that isn't 0, pi. Say omega t equals pi. Solving for t, we have pi over omega, which is just 9.90 radians over seconds. That equals 0.317 seconds. All right. So we found the maximum velocity. When that maximum velocity occurs, maximum acceleration, and when the maximum acceleration occurs. We are able to sort of pick out on this simple harmonic oscillator the values that we want just from that one function given above. All right. We've looked at the motion in a simple harmonic oscillator. Let's now look at its energy. So energy in simple harmonic motion. Again, I'm always going to try to go back to the same example. We have that spring that's constantly moving back and forth, and there's no friction. It's going to be moving at the same rate forever, at the same frequency, the same angular velocity. What is the energy of this system? It's think again of, this is the only spring I have of my picture. I had it horizontal. It was going back and forth like this. So imagine in this case, what is the potential energy? Well, we have the elastic potential energy from the spring itself. Yeah. So we have the elastic potential, which is, we're going to start using the term or the variable u for elastic potential, or I guess for potential, for any type of potential. U is 1/2 k x squared, and remember the k, that was the spring constant of whatever spring you're using. And for kinetic energy, we had K, capital K, which is just 1/2 mass times velocity squared. How do we relate these energies into something that is oscillating back and forth forever? We're not saying, in a lot of our other problems, we had a spring that was sort of stretched a bit. And then the question was like, what is the energy in this system? What is the force? And they left the problem right there. How does this energy, well, what if I let it go? And so it's going to snap back. What if I let it go and I want to find the energy somewhere in the middle here? I wanted to find the energy right here, or the elastic potential energy right here, or right here. How can I describe this? So we have this new way of describing these energies. One half Ka. This is sort of the amplitude of its motion. Cosine squared of omega t delta. This is the potential. In simple harmonic motion. And we have the kinetic energy. So that's also related to the spring constant of the spring. All right. And just like before, the total mechanical energy is just adding up all of the available energy of the system. So that's just U plus K. And in this case, if I add these two together, so it's going to be cosine squared plus sine squared. And if we sort of, factor that out, put it over to the side, cosine squared plus sine squared, that equals 1. And then what do we have left? We have this term out front that's sort of left over from those two. This is the lowercase k for spring constant. Try to make this all. There we go. All right, let me try to make sense of these equations here. Again, I haven't derived these. I'm just sort of placing them in front of you guys. Let's see if we can figure it out. We have, oh, it's too big. There we go. Okay. All right, so we have this. That's gonna bother me. Let's go like this. There we go. We have the position versus time graph. This is our graph we've seen before, except now I've compressed the spring at this specific moment. It's up here, it's at the top of its amplitude. And it's just moving along with its consistent rate. What if I want to find its potential energy right at this moment? Right at this moment right here, when it's compressed all the way in this in its path. Well, as we've seen before in when going over springs, when the object is compressed, when the spring is compressed, there's a large elastic potential. Also, imagine when the spring is compressed all the way and is beginning to change direction. At that very, highest moment, when it's compressed to its maximum, it's not moving anymore. It momentarily stops, and then it changes directions. So there'll be a maximum right there at the highest point. Right there. So we have this point of compression right here. Well, and what about down here? We have this, it would be a picture kind of like this. That would be just a bit more. It would be stretched out all of the way at this point. So we have another case where it's changing direction, and for a brief second, it is not moving. So all of its energy is elastic potential energy. So that's why we see a peak down here, right here in the middle, and we also see a peak right here and right here. From the same logic, when it's at these end points, it's changing direction and it's not moving. We could say when it is let's see if I get it going. When it's in the middle, when it's directly in the middle, it is moving its fastest. And it is at the equilibrium position right here and right here. Since it's at the equilibrium position, there is no elastic potential energy. So looking at here and here, we see how that relates to the kinetic energy down here and down here. Now there's a maximum right here at these two positions. All right, so I'm going to write some notes on this for people looking at this page later. So we have this side view. Simple harmonic motion, position at any given time. And it's going from A to negative A over a course of time. All right. Let's do this one down here is the potential energy. Let me zoom in so I could write clear. We have whenever stretched or compressed. Potential is a maximum. And for the kinetic energy, I'll say whenever passing through equilibrium point, kinetic energy, or I'll just say kinetic is a maximum. And you can see that the energies I have listed here, they're all positive. So the origin is right here. So how can we express the total mechanical energy? Well, total mechanical energy is just U plus K. And if we add these two graphs together, maybe you could see that they would add up perfectly. They would add up perfectly. I'm just going to draw it on this one and form a solid straight line at a amplitude of A. Or, I'm sorry, at an amplitude of 2A. See, this one goes to A, these go to 2A. Yeah. And I'll put over here how do I want to, right here is E total. E total. Yeah. And right here in the middle, that is the average. That's just half of E total. This is K average. Okay. All right. I'm going to do one more example. And I think that will be it for today. Looking at the energy of a simple harmonic oscillator. So a 3-kilogram object is attached to a spring and it oscillates with an amplitude of 4 centimeters and a period of 2 seconds. What is the total energy? What is the maximum speed? And at what point or at what position x is the speed equal to half its maximum value? All right, so starting out, we can do the total energy. We know an equation for this. It says E is related to a spring constant and an amplitude squared. Amplitude squared. There we go. Are we given a spring constant? Not quite, but we have enough to find it. Squared. This equals mass times its 2 pi over 1 period. Just inserting what we know about the angular frequency. Okay, and then just placing this right back into that equation. E equals 1/2 m 2 pi over t squared a squared. And that is now just 1/2 3.0 kilograms 2 pi over the period of 2 seconds. All of that squared times an amplitude of 4 centimeters. Again, I don't really like keeping the results in centimeters, so 4 meters. And it's good to transfer into meters anyway, because our value for the answer is going to be joules. And we need the SI units for this conversion. We get E, the total energy, E equals 2.4 times 10 minus 2 joules. All right. So total energy, what is the maximum speed now? So maximum speed is at one instant when the spring is oscillating, remember back to that graph, at one specific instance, the kinetic energy was all of the energy in the system. So that would also be the maximum. So I'll say 1/2. I can, we can phrase it like, E equals U plus K again, equals 0. Like this. And then I'll go and put in yeah. I'll say 1/2 E max squared is equal to E. All right, and we've just found the total energy, so this is good. That's 2.4 times 10 to the minus second joules over the mass, which was 3 kilograms. We get a maximum velocity of 0.13 meters per second. Okay. Next up, I know I'm going to run out of room, so let's shrink this down a bit. Next up, at what position x is the speed equal to half its maximum value? All right. At what position x? So thinking about how I found the maximum velocity right here. I just said that's, zoom in a bit. So I said that's potential energy 0 while it's moving its fastest. And so it's going to be completely all kinetic energy. Now for this specific part of the problem, we want half of its fastest velocity. So that means there's still going to be some potential energy left over. It's going to be some potential energy, it's going to be some kinetic energy. So we have E equals U plus K. That'll equal 1/2 kx squared plus 1/2 mv squared. All right. So this is actually a good start because it places in a position term, x, that we can maybe solve for in a bit. We need to find the position at half of its maximum velocity. So let's multiply in a half, 1/2 term in here. Okay, let me go like this. Equals 1/2 kx squared plus 1/2 m, not just v squared. I'm going to go like this. 1/2 v max squared. Yeah, I can just take, I can't just take it out directly. I still have to square that 1/2. So let's keep going. Kx squared plus so it's just 1/4 times 1/2. I'm just going to show it like this. So I've squared that 1/2 and then I just dragged it out in front. And this is actually, yeah. No, I'll do it right here. This is actually, keep going, 1/2 kx squared plus 1/4 e. Now, why did I change this term that's in the parentheses to e? Well, at the maximum velocity up here, I said k was equal to e. So we have this term right here, that is kinetic energy. I'm just going to call as e, since I already have that. That's already a known value to me at this point. All right, what else? E equals 1/2 k x1 squared plus 1/4 e. Let's rearrange this so it'll be a bit more clear what we're solving for. We want to solve for this x, this position. Fourth e minus e. Then I'd have to multiply everything by 2. Did I do that right? Yeah. 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 Hold on. Yeah, we're good. So we'll say that at this point, we have a way to solve for x. I'm going to just jump straight down to it. Plus or minus 3e over 2k one half ka squared times the amplitude. Okay. And just about there. Finally, we have equals minus root 3 over 2 times 4 centimeters. Equals plus or minus 3.5 centimeters. So that does it. So now we have this new way of using the energy of a simple harmonic oscillator to determine speeds, positions, accelerations, and whatnot. I think that is it for today. I hope to finish this chapter by tomorrow. So I'm going to cover some like real world examples. I think we'll finally go over some pendulums tomorrow. And then I think we might be done with simple harmonic motion. Yeah. So as always, if you guys have questions, just let me know. Otherwise, I'll see you later. Have a great rest of your day.